So good morning, everyone. My name is Gilberto Berardinelli from Aalborg University in Denmark, and I'm the coordinator of the Hexa-X-II project that is focused on INEX subnetwork. So to a large extent, this presentation will reflect the vision and the ideas that we have in our Hexa-X-II project. Just some quick fact on the project. Just a second. Okay. Yeah. Some quick fact of the project. So SHINE stands for Short-Range Extreme Communication in Entities. This is one of the Smart Network and Service Joint Undertaking projects for StreamB, Communication Infrastructure and Devices. And is the first project entirely focused on INEX subnetworks with the goal of pioneering new technology components for short-range communication with demanding performance requirements. The project started in March 2023 and is expected to last till end of August 2025. Our consortium includes 12 partners with a pretty good blend of expertise of industry, academia, and research institutions. So what is the project about? We know, and also many speakers in previous presentation have presented 6G as a network of networks. So 6G is expected to integrate subnetworks having very diverse capabilities in terms of spectrum, operational range, services to be supported, ranging from macro, micro, pico networks to non-terrestrial networks, network of drones, and so forth. At the very end of this broad landscape, in our vision, we have what we call INEX subnetworks that are short-range, highly specialized low-power cells that can be installed in entities like robots, vehicles, production modules, but also consumer entities like classrooms to deliver highly specialized and high-performance connectivity. For example, industrial subnetworks can be used for closed-loop control in robots and production modules. In-vehicle subnetwork can replace part of the wired control infrastructure in a car for motor control, braking, or other sensors, and making it wireless. Consumer subnetworks can be used for extended reality type of applications for education, but also for gaming and entertainment. In general, applications and use cases might be very diverse. A common characteristic is that performance requirements might be significantly beyond what can currently be supported by existing.
Gilberto, I will mute all, and then please you need to unmute yourself after that.
Okay, just a Can you hear me now?
Yes.
Okay, I'll just share full slide again in presentation mode. So as I mentioned, the application for subnetwork can be very diverse. A common characteristic is performance requirement beyond what can currently supported by existing radio technologies, and therefore innovation is needed. Another characteristic is that subnetwork can spontaneously become very dense. For example, if every robot, every car becomes a wireless network per se, and then we are in a factory with many robots or in a congested road, then we are having a huge amount of subnetworks, and therefore interference is a major problem we need to deal with in our radio design. So one may wonder, why do we call them subnetworks instead of tiny networks or very small networks? And the reason is that, as also anticipated by one of the previous speakers, subnetwork should be able to operate standalone because they may support services that cannot be interrupted at any time. But on the other side, they are also part of a larger 6G network. So they can benefit from connection to a wide area or enterprise parent network. For example, the parent network can aid radio resource management of subnetworks in its coverage area, but can also help traffic steering, service discovery. It can push the most advanced authentication and authorization framework down to the very low level of devices in a subnetwork. Also, subnetworks can be not only task-specific, but also time-bounded. So the parent network can eventually take care of setting up a subnetwork and revoking a subnetwork. One may think that within a subnetwork, we may have different traffic types. Some of this traffic can be highly critical. When I say critical, it's not only in terms of reliability, but also, for example, in terms of privacy, while other traffic may have more relaxed requirements. So the critical traffic stays within the subnetworks, while traffic having a more relaxed requirement can eventually be processed in an edge cloud or in a central cloud. So this way, even if the connection with the parent network breaks, the critical functionalities can still be running in the subnetwork. So given this general context, very briefly, what are the main objectives of the 6G Shine project? First is to define relevant application scenarios, use cases, and architectures for in-X subnetworks, and analyze their related performance requirement. Second is to design novel radio enablers for extreme communication in subnetworks and their integration in the larger network of networks. When I say radio enabler, I refer to physical layer, MAC, but also radio resource management and architecture. And the idea here is that we are going to leverage specific characteristics of the in-X deployments.
Great. First of all, apologies. It seems we had some issues in the connectivity in the building. I hope now it will work. So I will just start from when I was interrupted. So I've been introducing the general context of in-X subnetworks. During the first year of the project, partners have been working in defining potential use cases for in-X subnetworks.
Interruption, at least here it is not seen in the presentation mode, so I don't know if it is another screen or if there is a long delay, but
what about now? It's the same?
At least not yet, so the same. So we can see the slide 6 at the moment from your presentation.
Yeah. Okay, I'll try to continue, and hopefully at some point it will representation mode. So basically, partners are defining different use cases for subnetworks, dividing for consumer, industrial, and in-vehicle categories. For example, for consumer subnetworks, we are looking into immersive education, indoor interactive games, virtual live production, and augmented reality navigation. For the case of immersive education, I give just a quick example. It can be the case of a classroom where students are equipped with XR devices, for example, glasses, and a certain XR media content is streamed from a server to the students. So most of this content can be shared among the students, but then each student may require some individual update. For example, looking at a certain scene from a given point of view, or having a deeper dive into a given aspect of the scene, and the system should be able to quickly adapt to the user requests. Regarding industrial subnetworks, we have typical use cases as identified, for example, even by 3GPP regarding control of robots, unit test cell, and the visual inspection cell. But also the case of subnetwork coexistence in the factory floor, where we have, for example, multiple robots that form a subnetwork and they need to work together for a common task. And we see here a good alignment, of course, with the collaborative robots use cases in Hexa-X-II. In-vehicle subnetwork, as I mentioned earlier.
Sorry, Gilberto, it's still slide 6, not in the presentation mode.
Yeah, but I'm still in slide 6, yes.
Yeah.
Maybe I can enlarge a bit, but okay, if there are some issues. Yeah, regarding in-vehicle subnetwork, as I said, we refer to the case where part of the control infrastructure in a vehicle is replaced by wireless. So modern control infrastructure in a car consists of multiple control zones that are located in different positions of the vehicle. And then these zones can communicate with a central processing unit. The idea is that some of the connection in a car, like for example, between sensors and the zone controller or between the zone controller and the central processing unit can be replaced by wireless. So at the end of the month, we are submitting a deliverable where we explain in detail all the use cases along with the expected performance requirements. So if you're interested, check out our website. So regarding innovation, as I mentioned before, As I mentioned before, we consider innovation at different layers, including low layers. And some of our ambition and innovation can be relatively short-term in the sense that can be seen as incremental to what we have in current 3GPP releases, while other innovation can be seen a little bit more futuristic and having a longer-term impact even beyond release 20. For example, for what concerns a physical layer, we are looking into the potential of having antenna arrays and panels for subnetworks, also considering a different form factor in the device, for example, in the glasses. And the motivation for having antenna arrays and beamforming is not, of course, coverage, but is more, let's say, improving spectral efficiency and improving resilience to interference. We also believe that the area interface of some networks, especially for the very challenging use cases, must be natively robust to jamming and to external and malicious interference, for example, by leveraging frequency hopping for both control and data channels, but also by using enhanced detection and mitigation techniques. Also, when talking about short-range communication, it is quite natural to consider high carrier frequencies, given also the larger variability of spectrum. But on the other side, we are also aware of the demerits of high carrier frequencies. So one partner in the project is actually studying a different architecture at sub-terahertz and addressing the trade-off between throughput and energy consumption. A bit more future term, we look into solution for self-conjugating metasurfaces for short-range joint beamforming and communication. So those metasurfaces are a particular type of antenna array that is able to automatically retrodirect an incoming signal in the same direction. And when retrodirecting the signal, is also able to modulate the signal. So this can be seen as a promising solution for low-cost devices because it may not even require a digital to analog converter. Plus, it also eliminates all the delays associated to beam alignment. If we look at the MAC on a more incremental perspective, we look into enhancement for low latency, for example, considering proximity grouping. So devices in the subnetworks are expected to be located close to each other, which means we are also expected to experience similar radio conditions, and we leverage this property for reducing, for example, channel quality indicator reports and amount of signaling. And also we look into solution for enhancing configured grant for support of different periodicity in the subnetwork. We are also looking into predictive schedulers that can be based on context information or knowledge of underlying application and service. For example, if we are using a subnetwork to control a robot arm and we already know what type of position the robot arm may take, we may be able to anticipate what will be the radio condition and then pre-allocate resources accordingly. Another relevant topic is multiplexing of services with different requirements. So within a subnetwork, we may have, for example, high data rate traffic, like video, combined with periodic traffic, like for robot control. And this means those services may require a different uplink and downlink switching point. And we see that the flexible or full duplexing capabilities at the central node in the subnetwork can be beneficial for handling traffic, having a different uplink and downlink switching points. Also, we look into solution for improving reliability in a subnetwork. In spite of the short-range communication, we may have a blockage in a subnetwork, and this might be a serious concern, especially at high carrier frequencies. So we are looking into solution where subnetwork nodes can provide redundant radio link to a certain device in order to enhance reliability. So this is not fully exhaustive, of course, of the innovations we foresee for the low layers in Subnetwork, but this is mainly what we work on in the CG Shine project. And the general idea is that we are not somehow reinventing the wheel, but we, let's say, leverage specific characteristics of the short-range communication for innovation of physical layer and medium access control. If we go a little bit up and look into radio resource management and operation management, partners in the project are working in defining a new nomenclature, but also new roles and communication modes for subnetworks. For example, within a subnetwork, we can have subnetwork elements that can be low-cost devices like sensors and actuators. We may have low capability devices, for example, relays, and high capability devices that are able to have significant networking capabilities and are able to interface with the parent network. For example, a high capability device can be a UE that can be instructed by the parent network of setting up dynamically a subnetwork. So within a given entity, like a classroom or a production module, we can have one or more subnetworks where each subnetwork may consist of the element mentioned here. And those elements may eventually also be configured to dynamically communicate with each other. So in general, the nodes in the subnetwork can have flexible roles in coordinating and combining the communication links. And we are looking into novel distribution of control and data plane functionalities. As I mentioned before, some networks can also spontaneously become very dense, like robots in a factory, for example, and interference becomes a major problem to deal with. One of the previous speakers from CCIAN was already touching upon this aspect. So when looking about interference management, centralized solution refer to the case where the network takes care of, let's say, managing resources of the subnetworks in his coverage area. But this is not, of course, a very scalable solution. Plus, it is limited by the quality of the communication link between the subnetwork and the parent network. So in the project, we are actually exploring some hybrid solution where part of the decision-making capabilities is on the parent network and part of the decision-making capabilities is also in the individual subnetwork. And we're also exploring AI methods for enabling this. We look also into dynamic spectrum sharing between CG network and subnetworks. So in certain use cases, subnetworks may operate over different spectrum than the parent network, but other cases, for example, a private CG network may need to share the spectrum with the subnetworks. So we are looking into approaches on how this can be made possible on a dynamic manner. Also, the computational load of subnetworks might be in some cases quite heavy, like for example, of the XR processing. And we look into solution on how to offload part of the computational load to the edge or to the cloud. So how to make this fast and dynamic. Okay, so just to summarize, in our vision, when for supporting very demanding communication requirements, we need to go local, to go in X, and in our view, subnetwork is the way to go. So subnetworks are short range, low power cells, highly specialized with potentially demanding requirements in terms of data rates or determinism or reliability. And as I mentioned earlier, they can mainly represent an architectural innovation. So they should be able to operate standalone, but can benefit from connection to a CG parent network. And the parent network can be also the one eventually establishing dynamically or revoking a subnetwork. So in the project, we are working into three main categories, industrial, in vehicle, and the consumer. There could be more, for example, healthcare and so on, but this is what we are focusing on in the project. And we believe that we require significant innovation in low layers, but also radio resource management and network architectures for achieving the performance requirements of subnetworks at a low cost. So this is pretty much all. I apologize for the connection issues we have here in Aalborg. Hope I managed to convey the message anyways. Thank you. If you are interested, visit our website, sign up for the newsletter, and follow up on the social media. Thanks.